Okay, Dr. Roha, you can start.
Okay. Um, Assalamualaikum warahmatullahi wabarakatuh. Good afternoon and selamat sejahtera to all the respective audiences. Let me introduce myself. I'm Roha Abdul Majid from SKT, and I am your MC for the session today. The session will begin with the opening remarks and biosketch recital by Datuk Prof. Dr. Muhammad Rafiq bin Abdul Qadir as the chairman of the session, and followed by the professorial inaugural lecture given by Prof. Dr. Azman bin Hassan. And later, the content of the lecture will be reviewed by Dr. Harintara Vimal Balakrishnan from Prolexus Berhad. Before that, a quick reminder, we will end the session at 5 p.m. Probably we can entertain some questions at the end of the review session. To save time, I strongly recommend for the viewers or audience to write the question in the chatting box. Therefore, you can leave the screen later with the satisfying answer. And of course, don't forget to claim your CPD points during the session. Without further ado, I will pass the screen to Dr. Muhammad Rafiq to chair the session.
Thank you, Dr. Roha. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 104th Professorial Inaugural Lecture. So I will read the biosketch of our professor today. Professor Dr. Azman Hassan is a professor at the School of Chemical and Energy Engineering, University Technology, Malaysia. He obtained his PhD in Polymer Technology from Loughborough University in 1997 and was promoted to professor in 2007. He has held various administrative posts such as the head of Polymer Engineering Department from 2002 to 2008, Deputy Director Research and Publications for Research Management Center 2008 to 2011, Director for Research Publication Center 2012 to 2014, and Deputy Dean for Research and Innovation at the Faculty of Chemical and Energy Engineering 2015 to 2017. He is elected as a member of UTM Senate since 2011 as Vice President of Perintis, that is Persatuan Saintis Muslim Malaysia, and Vice President of Malaysia Polymer Society. He was appointed as Malaysia Quality Assurance Head of Accreditation Panel at University College Tati and UITM Perlis, External Examiner for Polymer Engineering Program in UNIMEP, Evaluation Panel Member for Grants under MOHI, Ministry of Higher Education, and MOSTI, Ministry of Science, Technology and Innovation, Malaysia. He is a fellow member of Plastics Rubber Institute of Malaysia, PRIM. His achievements include Top Research Scientist Malaysia TRSM awarded in 2016 and 2 gold medals at Pachipta and Inatex. He was listed in the top 2% most highly cited researcher in the world for 2019 based on research paper by a Stanford University expert. His paper published in Materials and Design received the most highly cited paper award in 2019 in UTM. He has supervised over 30 PhD students, published more than 250 papers with a Scopus H index of 37, granted 2 patents and 1 utility innovation, and principal investigator for more than 20 research grants, including an international grant from Qatar University and a contract research from Nano Malaysia in collaboration with Proton. He has edited 2 books and written 30 book chapters. He is an editorial board member of Fibers and Polymer and Journal of Plastics Elastomers, Web of Science Index Journal. And currently, he is the editor-in-chief of Perintis e-Journal. So, without further ado, here is Professor Dr. Azman Hassan for his inaugural lecture. Over to you, Prof. Azman.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. And a very good afternoon to Chairman Professor Datuk Rafiq, who is also the Dean of Engineering, to Associate Professor Dr. Raha, who is the Master of Ceremony for today, and to Dr. Hyrin, the Research and Development Manager, Prolexis. Ladies and gentlemen, thank you very much for being here to my inaugural lecture with the title Enhancing Polymers, Meeting Societal and Industrial Needs. I am from the School of Chemical and Energy Engineering and also attached as research fellow at the Center of Advanced Composite Materials, one of the Center of Excellence in UTM. Briefly, I would like to start by introducing my family. I have 3 sons and 3 daughters-in-law, and currently I have 10 grandchildren. But if you see in the picture that was taken in 2018, there were only 6 grandchildren, and 3 more were born after the year of 2018, and now we have 10 grandchildren, including 1 eldest granddaughter who is not in the picture now. Now, introducing my family with my father. This picture was taken 20 years ago. I am the 5th child with 3 elder brothers, 1 younger brother, and 1 elder sister. Now my father is 91 years old, and my mother is 84 years old. Now is picture with my students in 2012. You can see here the students are from various countries. They are from Iran, from Pakistan, from Iraq, from Nigeria, and of course from Malaysia. And I am happy to mention that most of them are very successful in their career, and 2 of them are now professors in their universities. Let me now introduce a little bit about the Center of Advanced Composite Materials, which I am one of the research fellows. There are 9 members, 9 research fellows, which is being led by Associate Professor Dr. Shukur Abu Hassan. The vision of CACM is to become the strategic national research and teaching center in composites technology. That means we are not only aiming to become the research center, but also to become the teaching center in composites technology for Malaysia. And CCM has expertise ranging from blast and ballistic structural composites and to high temperature performance advanced composites. And one of the most successful projects that was being carried out is the composite materials for structural engineering from thin slag polymer concrete. The presentation outline for my lecture today, I will start with properties that make polymers unique and special. Before that, I would like to explain the relationship between plastics, rubber, fibers, and polymer. Polymer are molecules composed of many repeating smaller units, and it can be used as plastics, as rubbers, and fibers. I would like also to share about a scene in a film, The Graduate, which was released in 1967 about Ben, a college graduate who is talented but aimless. Mr. McGraw is a wise man, educated man who has advised Ben. And among other things, Mr. McGraw has said, there's a great future in plastics. Think about it. Will you think about it? So this is a scene from a film Graduate mentioning that there is a great future in plastics. What are the specialty of plastics? Compared to metals, plastics have the advantage of low density, ease of processability, corrosion resistance, thermal and electrical insulators. But one special thing which I have found out that plastics can be used to make items that have no alternative from other materials. For example, in the medical application, where we need the materials to be transparent, as well to be flexible and to be light. And the other property, which is very much related to my talk today, is that plastics are easily modified through blending and through the incorporation of additive. What are the benefits of plastics product? By using 22% of carbon fiber reinforced plastics in Airbus A380 double decker, it was found that we were able to save fuel and lower the operating cost by 15%. And if we do not use packaging, the weight of the packaging would increase by as much as 400%. And I also would like to quote from Lord Alexander Todd, who is the recipient of Nobel laureate in 1957. He said that I am inclined to think that the development of polymerization is perhaps the biggest thing that chemistry has done, where it has the biggest effect on everyday life. And Hermann Schrödinger was the one who proposed the concept of macromolecules as large molecules linked together by covalent bond. And he is also the recipient of Nobel laureate in 1953. Moving on, now I am going to move to the second section on the societal and industrial needs. What are societal needs? Societal needs are the essential needs for the survival and the progress of the society. Example of societal needs which are related to my lecture today is about food packaging, health protection in terms of biomedical application, transportation, health, shelter, and safety. What are industrial needs? Related to my talk today, industrial needs are to produce materials which has the desired combination of properties that can be processable at a moderate cost. From the mechanical properties point of view, one of the aim is to achieve balance of stiffness, strength, and toughness. Now I would like to quote 3 examples of outstanding polymers that meet societal and industrial needs. Number 1 is nylon, Kevlar, and Zylon. The invention of nylon is a breakthrough. It was invented in 1934 by Wallace Carothers from DuPont Chemical, and the invention and the development of fiber spinning process is a game changer that enabled the production of highly oriented nylon fibers. And nylon has been used to make nylon stockings, which changed the world. When the stockings were released for sale for public on May 15, 1940, the demand was so high that in the first 4 days, 4 million pairs were sold. No other product has enjoyed immediate, overwhelming public acceptance similar to this product from DuPont nylon. And nylon has contributed very significantly in the World War II, which took place from 1939 to 1945. And the military used it in production of 3.8 million parachutes and 500,000 aeroplane tires and uncounted numbers of glider to ropes and vests. What makes nylon special? From molecular point of view, hydrogen bonding can be formed by the hydrogen from the amide group and the oxygen from the carboxyl group. And having hydrogen will influence the stiffness, the crystallinity, and glass transition point of the material. Secondly, I will be talking about Kevlar. Kevlar is an excellent anti-ballistic material because it takes a great deal of energy for a bullet to pass through. It was invented by Stephen Kowalski in 1965. Thirdly, which is relatively less known, is Xylon, the world's strongest synthetic fiber. It was being developed by SRI International in 1980s and manufactured by the Toyoba Corporation. It has the tensile strength of 1.6 times higher than Kevlar, and the Young's modulus is stiffer than the steel. Because of these excellent properties, Xylon has been used for military and also for the aerospace application. And now we are in the era of COVID-19 pandemic, and polymer has contributed a lot in this field. The health regulatory bodies such as World Health Organization have laid down strict protocols for the healthcare workers, such as personal protective equipment. And amazingly, these PPEs are made of plastics. And very soon, we will be able to use transparent masks composed of polymers fibers 100 nanometers apart, which is small enough to filter the virus and the bacteria, but big enough to allow the air through. This research are currently being done by the researchers at Switzerland's Federal Institute of Technology at Lausanne. I would like also to share an incident which happened in 1986 about the Space Shuttle Challenger disaster. The Space Shuttle Challenger broke apart 73 seconds into its flight, killing all 7 crew members aboard. What is the cause of this disaster? The cause of the disaster was traced to an O-ring, a circular gasket that sealed the right rocket booster. The failure was because the temperature during the launching time was at 30 degrees Fahrenheit, but the engineers have advised NASA management to only use if the temperature is above 57 degrees Fahrenheit. So the lesson that we can learn from this incident is that the society and the industry needs to know the limitation of the material to be used, and polymers is a material which is very sensitive. The properties are very sensitive to the changes in temperature. Some would be very significant change, and certain properties will only be a minimal change. Thirdly, now I am moving to the methods for enhancing polymers. There are three methods, namely by using additive, by blending, and by synthesis. What is a polymer additive? Polymer additive is a material added to polymer to improve their processability, performance, and appearance. And the market is very large. And in 2020, the market is 57.8 billion. And it can be of various forms, plasticizers, impact modifiers, flame retardants, and so on. Polymer additives fall into three general functional clusters. Those which are essential for processing, those which enhance properties, those which correct problems caused by other additives. For example, if we want to improve the flame retardant of a polymer, we have to add flame retardant. But the addition of flame retardant may deteriorate other properties such as impact strength. So the addition of impact modifiers are needed to improve and to correct problems caused by the initial addition of the flame retardant. And the incorporation of additive makes polymer material suitable for various applications in automotive, packaging, construction, electronics, and telecommunication. A quotation from Josh Put, the Vice President of R&D Material DSM Research. He said that additives play a leading role in the success of commercial plastics, elastomers, coatings, and adhesives. Without additives, many polymers would simply of limited use. A good example is PVC. When PVC was invented, it cannot be used because of the low thermal stability, which is almost the same as the processing temperature. Then it can only be of use when the scientists develop the heat stabilizer that can stabilize PVC during processing. The next method for enhancing polymers, which I would like to discuss today, is polymer blends. Polymer blending is the mixing of at least two polymers to produce new materials with quite different properties. And polymer blends have shown a growing development due to the wide application in various sectors such as electronics, packaging, and automotive. It represents more than 20% of the total consumption of engineering polymers, and the market is expected to increase over 50 million tons per year. Polymer blending is more advantage to develop new polymers compared to the development of new monomers because it is cheaper method and less time consuming. And also materials from polymer blends can be tailor-made based on the proportion and the ratio that we blend. We can produce materials of various properties. Although polymer blending is combining of two or more different advantageous properties, so we expect we will be able to produce new material composed of both strength of each polymer. But in reality, it's not always the case. This is because there is an inherent incompatibility between the two polymers to be blended. Therefore, there is a need for a third component, which is called compatibilizer, to improve the compatibility and also the miscibility between the two polymers. Therefore, in order for us to develop polymer blend successfully, we need to have a clear understanding of few topics which are very important. Number one is the concept of miscibility. We need to know the factors that influence the miscibility and the immiscibility of polymer blends. Why certain polymers are miscible and why certain polymers are immiscible. Secondly, we need to know about the morphology. There is which polymer will form the dispersed phase and which polymer will form the continuous phase, and how big is the dispersed phase in the continuous matrix, because all these factors will determine the properties of our polymer blend. Thirdly, we need to know about blend compatibilization, the process of the interfacial properties. If the original polymer blend are immiscible, how we can use the compatibilizer to improve the compatibility between the polymer blend. And fourthly, we need to understand the base and added polymers. What are the strengths of the base polymer and what are the limitations of the base polymer, and how will the added polymers will be able to overcome the limitation of the base polymer. So with this deep understanding of the four topics, we will be able to produce polymer blends which will be able to be commercialized. One example of a successful engineering polymer commercial blend is the blend of polyphenylene ether and polystyrene. If we were to look at the molecular structure, we can see that both polymers have the aromatic structure, and this will promote the possible compatibility between the two polymer blends. Polymer PPE has good properties in terms of having excellent heat resistance, good dimensional stability, and excellent mechanical properties. However, PPE has the limitation, and one of the most important limitation is it has high melt viscosity, which make it very difficult to be processed as a commercial molding resin. And this can be overcome by the use of polystyrene, which improve the processability of PPE. And if we use high impact polystyrene, then we will also be able to improve both processability and the impact properties of this blend. And the versatility of PPE high impact blends has been proven that it is unparalleled commercial success, accounting for nearly 50% of market volume of all engineering polymer commercial blends. And this PPE HIPS blend has been commercialized under the trade name Noril. And the company that is currently commercializing this product is SABIC, a Saudi petrochemical plant. And it is used mainly in electrical housing, switches, medical application, automobile parts, and building components. And most well-known Noril was being used for the housing of the Apple II computer. And one interesting thing that I would like to share this afternoon is that in a fire, the plastic convincingly proved its heat resistant. After extinguishing the fire, it was found the computer casing was almost melted, but not completely. And after cooling, the housing was removed, and interestingly, the motherboard was still functioning. And Steve Jobs and company leveraged on this and built an entire advertising campaign around it. Now I am moving to the next topic on enhancing polymers, the journey and contribution. That is my own experience in enhancing polymers. Over the past 20 years, I have received 81 grants with 28 as the principal investigator, one from the industry, which is the graphene project with Nano Malaysia and Proton, one international grant from Qatar University, and 12 grants from national from the Ministry of Higher Education and Ministry of Science, and 14 from UTM. This is the number of papers and supervision which I have conducted. I have published 214 papers with each index of 37, and the Scopus citation is 5,614. I have supervised 33 PhD students and 23 have graduated, 43 masters, and 37 of them have graduated. In terms of intellectual property, I have 2 patents were granted with me as the co-inventor, and one is me as the main inventor on the polymeric composition novel toughened polylactic acid nanocomposite. And the innovation utility, which I am the main inventor, is from the contract research with Proton and Nano Malaysia. Along the way, I have received a few recognition as being mentioned by Dato' Rafiq as top research scientist Malaysia in 2016. I have received the award, I'm the recipient for the award paper with highest citations in UTM in 2019, and also from the work by a researcher in Stanford University, I have been listed as the top 2% cited scientist in 2019. This is the overview of my research activities. Mainly, I work on polymer nanocomposites, also on impact modified polymers, little bit on polymer blends, and polymer composites and biocomposites. In terms of properties, we have done together with the students mostly on mechanical properties, thermal properties, and in the last 5 years, we also have started doing research on flammability properties and little bit on electrical properties, also on anti-corrosion. I have one PhD student who has graduated, and we were also venturing in another properties about tribological properties on the wear and tear of material. In terms of application, my research aim for the application in pipes, in automotive. That's why we proposed the project on graphene to be used in automotive, in building, for electronic housings, for coating, and also for packaging. Okay, I would like to start talking about polymer nanocomposites. Polymer nanocomposites became an interesting topic when the work was being done by Toyota in 1991 on the layered silicate polyamide 6 nanocomposites. Polymer nanocomposites are a type of composite consists of nanofillers dispersed in polymer matrix. And these nanofillers can be of different shape, can be in platelets, in fibers, but one of the requirements is that one of the dimension of these nanofillers must be less than 100 nanometers. What are the benefits of nanofillers? Owing to the nano size features, it can give very high surface to volume ratios, and because of this, they possess unique combination of multifunctional properties. And the nanoscale distribution of such high aspect ratio fillers can bring various improvement to the polymer matrix in terms of mechanical properties, flame retardancy, and gas barrier. And compared to microfillers, one of the specialty of nanofillers, it only requires low concentration between less than 5 to give the properties enhancement. And one of the areas that we have pioneered in UTM is the toughened polymer nanocomposites, where we studied about increasing the toughness of polymer nanocomposites, because the addition of the nanofillers will increase the stiffness of the polymer, but will at the same time decrease the impact strength. So we have made the study of toughening the polymer nanocomposites which were produced. And we have around 5 students who has worked on this topic on various polymer matrix and various nanofillers. The concept of toughened polymer nanocomposite. The main objective is to achieve a balance of stiffness, strength, and toughness. And as I mentioned, if we add nanofillers, we will be able to increase the stiffness, but at the same time we have to sacrifice the impact strength. If you look at the arrow on the top, and the arrow at the bottom shows the addition of impact modifier will increase the impact strength at the expense of decreasing the stiffness. So the desirable properties is that we want to optimize having balanced properties of stiffness, strength, and toughness. And one of the work which was being published in Polymer and Polymer Nanocomposite is the preparation and characterization of polyethylene octane grafted maleic anhydride toughened polyamide PP monomonolite nanocomposite. In this slide, it shows firstly is the blending of the polyamide and the polypropylene. There must be a reason why we blend polypropylene with polyamide. Polyamide inherently is an engineering polymer with high strength, but it has the weakness of low moisture resistant, low dimensional stability, and also it is relatively high cost. The addition of polypropylene in polyamide will improve the moisture resistance, and also it is able to reduce the cost. However, polyamide and polypropylene are immiscible. Therefore, there is a need to add compatibilizer, which is polyethylene octane elastomer, which can act both as impact modifier and also as compatibilizer. And this is the method to prepare the test specimen, firstly by melt blending in twin screw extruder, followed by the injection molding of the test specimen. In the twin screw extrusion, we need to ensure that there is good and uniform distribution of the nanofillers so that you will produce nanocomposite with good properties. From the results on the effect of the monomonolite content on the fractural properties of the nanocomposite, we can see that the addition of organoclay, which is the MMT, will increase the fractional modulus continuously, and it has increased by 300% with the addition of 10 weight organoclay. and the strength increased, reaching the highest value at 4 weight% organoclay content. However, it started to decrease above 4 weight%. The morphology or the distribution of the nanofillers is very important. What we want to achieve is nanocomposites with exfoliated structure. Secondly, is the intercalated structure. But if there is stacking of the nanofillers, then the good properties will diminish. That is the reason for the decrease of the fracture strength after 4 parts per 100. By using X-ray diffraction, we can see the morphology of the material. We can see that there is the formation of partially exfoliated and partially intercalated structures. As we increase the nanoclay content, we expect the relative fraction of the intercalation over exfoliation to increase with organoclay. And also we can see that ordered intercalated structure is still being maintained for nanocomposites even at high clay loading. On the thermal analysis, by using thermogravimetric analysis, we can see that the addition of the organoclay can increase the thermal stability of the nanocomposites. And the improvement in the thermal stability of the nanocomposites is attributed to the formation of char, which hinders the out diffusion of the volatile decomposition products. The next paper on this topic was being published in International Journal of Polymeric Materials in 2007. In this paper, we discuss about the comparison between the two types of compatibilizer, which is the polyolefin actin and also the PP grafted maleic anhydride. We can see that the POE grafted maleic anhydride is better in terms of improving the impact strength, but it is not as good as PP grafted in terms of fracture strength. This is because of the POE. Not only it can serve as a compatibilizer, but it also as an impact modifier, which of course will increase the impact strength and at the same time will decrease the stiffness of the material. And on the right, we can see the interaction between the octadisilomine group of the MMT of the organoclay and the reaction between the POE grafted PA6. And also we can see that we propose the formation of the hydrogen bonding, which is very good in enhancing the mechanical properties of the nanocomposites. From the morphological analysis, we can see the addition of the compatibilizer entirely change the surface. We can see the homogeneous fracture surface of the compatibilized PA6 PP nanocomposites, which indicates better adhesion between polyamide and the PP phase. When we use chemical to etch the fracture surface, we can remove the polypropylene, and we can see that the original structure of polypropylene actually decreased when we add the compatibilizer, and we can see the very small PP as the dispersed phase when we use the POE grafted maleic anhydride. This indicates that both compatibilizer is efficient, is effective in enhancing the interfacial adhesion between PP and PA6. And the next paper is to study about the possible use of the MMT as both to increase the flame retardancy and to improve the mechanical properties of the nanocomposites. In this study, we have partially replaced the magnesium hydroxide, which is flame retardant, by the same amount of MMT. We can see that by replacing part of the magnesium hydroxide with MMT, the fractional modulus of the nanocomposite improved, while the fractional strength is being maintained with increasing MMT. And for the impact strength, we can see that impact strength and the elongation at break improve slightly with the addition of MMT. Therefore, from that study, we can conclude that MMT can function both as flame retardant and also as reinforcement. And in our study on flammability test, we have used Cone calorimeter. Cone calorimeter is based on the fire testing principle that the amount of heat released from a burning sample is related to the amount of oxygen consumed during the combustion. And the amount of heat generated is directly aligned with the severity of fire. And I am happy to mention that we are among the first in Malaysia to use Cone calorimeter to study the flammability properties based on our networking and our collaboration with various universities in Turkey, in France, and in Spain, and also in Saudi Arabia. From the results, we can see that there is the reduction in peak heat release rate with the presence of MMT, and this is achieved due to the formation of the insulation layer, which becomes the physical barrier between the heat and the polymer. And we can see that as we increase the MMT inside the magnesium hydroxide, the insulation char, which form the physical barrier, becomes thicker and becomes more efficient in decreasing the flame retardancy of the nanocomposites, as shown in the decreasing value of the heat release rate. Next thing, I move on to graphene polymer nanocomposites. Graphene has been referred by the media as the miracle material of the 21st century. It was discovered in 2004 by two scientists in United Kingdom, Andrew Jim and Konstantin Novoselov, and they won the Nobel Prize in the year of 2010. Graphene can be considered to be a multifunctional additive because it is able to simultaneously provide a number of properties enhancement. Besides improving the mechanical properties, it also improves the thermal conductivity, the barrier properties, and also thermal properties, thermal conductivity, flame retardancy, and mechanical strength. And in terms of application, the potential application of graphene in Malaysia based on the market size, it is predicted that there is a good in terms of applicability to Malaysia and market size for rubber additive and also in plastics additive. So this is two of the areas which are related to our topic of our lecture today. And this is one of the papers published where we use graphene in the form of graphite nanoplatelets to reinforce polyethylene terephthalate polypropylene nano composites. And we can see from the results that the fractional modulus increased steadily with the increase of graphene loading, and it reached a maximum of 3 parts per 100 with a value of 38.7 megapascal. And also the nano composite shows the highest values of impact strength at 3 parts per 100, corresponding to the maximum concentration in which there is uniform dispersion of the nanofiller particle. And then there is a sharp drop of impact strength after 3 parts per 100, which is attributed to the restacking of the graphene due to the existence of the van der Waals forces between the graphene. At 3 parts per 100, we can see that the graphene or the graphite nanoplatelets were dispersed with no signs of agglomeration. And this uniform dispersion of graphene in the matrix is responsible for the enhancement of fractional and impact strength of the nanocomposites. The next paper is the one published in Polymer Degradation and Stability in 2014. The objective of this research is to determine the effects of graphene nanoplatelets content on the flammability and the thermal properties of polyethylene terephthalate polypropylene blends. Also, we can see that with the addition of graphene, the heat release rate decreased continuously. And this is an indication of the improvement in flame retardancy due to the graphene content. And if we inspect the char residues from the nanocomposites from the cone calorimetry analysis, we can see the formation of thick and compact residue layer, which act as the insulating barrier. And this formation of the residue layer is very critical to obtain the low heat release rate. And the thickness of the residue increased with the increasing graphene content. The next study with graphene is the use of hybrid fillers of the graphene and KNAF to improve the properties of polypropylene. From this study also, we can see the addition of graphene into the KNAF PP composite has increased the tensile strength by 60% with the incorporation of 3 parts per 100 of graphene, and the Young's modulus keep on increasing and reach an increase of 13% with the incorporation of 5 parts per 100 of graphene. And also, interestingly, the impact strength increased by 12% with the incorporation of 3 parts of graphene. From the results, we can see that the addition of both KNAF, which is natural fillers, and graphene was able to improve both the Young's modulus and the impact strength. The Young's modulus increased quite significant from 710 megapascal to 1220 megapascal, but only a marginal increase in terms of impact strength. Another study which we have done is the heat deflection temperature. Heat deflection temperature is a test where it is a combination of both heat and loading of mechanical force. We can see that in this test, we want to know at what temperature the polymer will bend at certain deflection. And we can see that also the HDT of the hybrid Knauf graphene composite increase with increasing graphene content, and the effect is quite significant when we use the 0.6 megapascal loading. This is because the mobility of the polymer molecules were hindered by the inclusion of the graphene nanofillers. By using transmission electron microscopy, we can see that, and we can confirm the homogeneous dispersion of graphene in the matrix at 3 parts per 100 content. Moving on to next research on the cellulose nanoviscous reinforced polylactic acid nanocomposites, which is being published in Polymer Testing. In this study, we have used empty fruit bunch oil palm biomass. And the chemical content of the oil palm biomass, it contains largely cellulose, which is 50%, 25% hemicellulose, and 25% lignin and extractive. And cellulose is a unique material due to the distinctive structure and properties such as hydrophilicity, biocompatibility, biodegradability, chemical stability, and also it contains reactive hydroxyl groups. Based on our study, we have proved that we were able to produce cellulose nanoviscous, which is confirmed to be nano in size. From the TEM, it is confirmed that the diameter is less than 10 nanometer and the length is more than 100 nanometers. Also, we have used the atomic force microscopy, and it is been shown that the cellulose nanoviscous individually have good aspect ratio was being produced. And we also studied the effect of this cellulose nanoviscous on the nanocomposites in terms of mechanical properties. We have seen that the Young's modulus increased significantly with the increasing cellulose nanoviscous, but there is a decrease in the elongation at break with the increasing CNW content, and also there is a significant increase in the tensile strength only until 3 parts per 100. And also we check the with transmission electron microscopy, and we can confirm there is good dispersion of the CNW in PLA at 3 parts per 100, and there is some aggregation of the CNW at 5 parts per 100 due to the interaction between fillers. This results in the decrease in tensile strength. And also interestingly, we can also show that there is no decrease in transparency with the addition of the cellulose nanoviscous. We can see that there is the transparency is almost similar between PLA, CNW nanocomposite, and the PLA film. The next research that is being carried out now from our FRGS grant is to produce synthetic wollastonite nanofibers using green hydrothermal synthesis. We want to determine the effects of the reaction medium, temperature, and time so that we will be able to manipulate to get the size of the wollastonite that we want. From our study, we have found out that the hydrothermal synthesis parameters can be manipulated to produce synthetic wollastonite nanofiber with various aspect ratios to meet the demand in different applications. And the reaction medium which produce the highest aspect ratio, the highest length of a diameter ratio is the one using 80% water and 20% ethanol, which is being heated at 200 degrees centigrade at 16 hours. And the synthetic wollastonite nanofiber will then be able to be used as reinforcement of fillers to improve the properties of polymer. The next research that was done by one PhD student who is currently waiting for his oral examination is the manufacture of graphene filled UPVC nanocomposites for mining application. One of the properties in the mining pipe application is that there is a tendency for the accumulation of the static electricity. So the aim is to produce a PVC pipe formulation which can ensure with good electrical conductivity while maintaining the good mechanical and rheological properties of the PVC formulation. And we have successfully determined a formulation by using a type of wax where we do a pre-dispersed graphene which can increase the electrical conductivity. And we have found that the properties of our graphene filled UPVC formulation is compatible, is as good as the formulation using carbon black of the commercially available formulation. And it has the advantage because we will only be using a little amount of graphene which will not affect the mechanical and also the rheological properties of the PVC formulation. Therefore, this level of conductivity which we have determined opens the door for the pre-dispersed graphene filled UPVC nanocomposites for mining pipe application in the future. I would like also to share our contract industrial research on the topic toughened graphene reinforced polymer nanocomposite, which we work together with Nano Malaysia and Proton, and we have filed an innovation utility improve polypropylene polyamide nanocomposites, and now Nano Malaysia is working with various companies to ensure the commercialization of these graphene nanocomposites and to be utilized in our Malaysian automotive industry. Also, I'd like to mention about the international grant research from Qatar entitled Recycling Polymers in Qatar. And from this research, we have produced 3 good papers done by 3 master's students. And also we have the industrial networking with Hyperseal Syndrome Bernhard. Our goal is to improve the mechanical, thermal, and rheological behavior of pressure-activated sealant pipes for oil and gas industry. And we have worked together and great impact on the development of the Hyperseal products and solution, especially in solving the problem of well integrity issues, saving life, assets, and environment. And Just recently, we received another grant, a knowledge transfer program grant from UTM as part of our community work on the project is the value added products from industrial waste and agricultural waste for secondary application. So we are working with the religious school to uh, to build bench and other furnitures using natural fillers reinforced with plastic composites. And now we are moving to the next stage on the current reality and the way forward. The current reality is that plastics, 300 million tons of plastics are being produced, and this causes severe environmental problems because plastics are not biodegradable materials. And in 2018, a Pacific Ocean garbage estimated to be the size 2 times the size of France has been observed. So plastics pollution is now everyone's problem. As said by the Vice President of the European Commission, Frans Timmermans, single-use plastics that take 5 seconds to produce are used for 5 minutes, then take 500 years to break down again. What is the way forward? The way forward is firstly to increase the application of bio-based and biodegradable polymers in our daily life. And these bio-based polymers can be produced from the agro resources, from the fermentation using microorganisms, or using from biotechnology, using lactic acid as a substrate to produce polylactic acid, and also other bio-based polymer such as polyethylene and polypropylene. Polylactic acid is considered to be one of the best bio-based polymer to be produced currently because of it is eco-friendly, biocompatibility, processability, and it is better than other bio-based polymers such as PHA and PCl, and it can easily use the twin screw extruder to be processed, and it is energy savings, and also it has good mechanical strength and properties. The properties are easily modified, similar to other synthetic polymers. And polylactic acid has very good future for biomedical application in various fields. Secondly, is the use of the environmental friendly, more efficient, multifunctional, and cost-effective additive. One of them is the use of non-toxic and environmentally friendly organic for PVC stabilizers, and also we expect more efficient nanofillers which are being functionalized for better compatibility with polymer matrix. As a conclusion, we can say that the impact of polymers on the present way of life is almost incalculable. Polymers, as I have shown, are versatile materials. It can be tailor-made using additive and blending with other polymers, and polymers will continue to play important role in meeting society and industrial needs. And the future trends, as I have mentioned, is the increased application of the bio-based and biodegradable polymers and the use of more effective additive, which is environmentally friendly, more efficient, and multifunctional. And as acknowledgement, I would like to acknowledge the Polymer Research Group my friends who are formerly from our polymer engineering department, my postgraduate student, the present one, consists of 9 PhD students and 6 master students. The past postgraduate students, and these are the pictures which I managed to gather. Postgraduate students, where they are now. So I am happy to mention that my postgraduate students are now all over the world. There is one working in Loughborough University, some are doing PhD in Sydney, working in Monash University, and there are few who have become professors in Nigeria and also in Iraq. And also acknowledgement to my collaborators who have helped me from various countries and also from various universities and institutions in Malaysia. Acknowledgement to the UTM Thought Management, School of Chemical and Engineering, Faculty of Engineering, the Office of Deputy Vice Chancellor, the Office of Corporate Affairs. And thank you for your time.
Dr. Roha, please unmute your mic, please.
Okay, sorry. Okay, thank you, Azman, for bringing us to venture into the polymer worlds. After this, like I said, I'm going to find that film to know the next conversation between Maguire and Ben about the future of plastic. Okay, next we will hear a review from Dr. Harintara Vimal Balakrishnan. He will review the content of the lecture given by Prof. Just shortly. So, Dr. Harin, I pass the screen to you. Dr. Harin, where is he now? Okay, there you are.
Hi everyone, can you hear me clearly? Yeah. Thank you, Dr. Roha. Good day to Professor Dr. Rafi, Dr. Roha, Professor Azman, the professors, academic staff of UTM, the management staff of UTM, the UTM students, and also my fellow lab mates from the Polymer Engineering Department. Right? So it's a great honor to be given the pleasure to convey the closure speech for inaugural lecture of my mentor, my master's and doctoral research supervisor, Professor Dr. Azman Hassan. So considered very grateful because out of these 80 plus students, so I got the opportunity to talk about one or two words and share my experience with him, previous experience with him when I was a student. Right? My time was with him was a student was from 2007 to 2013. So both my master's and my PhD projects were actually done through him. That was a long stint of time of 6 years. Right? So when I first came in to meet him, right, to ask for a position for research, master by research project, right? So after I obtained that, that was just a small joke. Right? So I asked him, so if it is by research, so when do I work? You know, so he told me you can work whenever you want, right? You can treat all your weekdays as Saturdays. You know, you can just work wherever you want. It's just after 3 or 4 months, I realized that I had to work on Saturdays as well. All right, that was the time. All right, so but it was a good experience. All the pressure and persistence that he gave me, finish my projects. Okay, that has enabled me to perform much better compared to my peers. Right. So today's topic: enhancing polymers, meeting societal and industrial needs. A title which carries much significance in the material world today. Undoubtedly, human society without synthetic and natural polymers is difficult to imagine. Right? Both types of polymers are extensively used in many applications, such as industrial products, packaging, medical science, transportation, clothing, electronics, communication, and even in defense weaponry. Right? And all this have been mentioned by Professor Azman just now. So through his sharing, we know that an academic career is not built in big leaps, but in small steps that involves so many others along the way. Right? We could see how Prof. Azman leveraged his intuition on the properties of polymers into a legacy that he has built over his career span as a distinguished researcher and academician. So I believe that a researcher's network and research ideas are actually enabled by encounters, right? Whether it could be chance encounter, small encounters, meeting at events, connections, that you develop into collaborations and also lifelong friendships, right? So through that, his networking skills, I mean, his network has been growing every year, and he became a very well-known man in his field of expertise. Right? People knew him wherever I went. Right? So when talk about conferences that I went to, I always had to carry the badge saying that I'm Prof. Azman's student. Yeah. So and the research is so wide, indeed, over time. 1 minute you think that you are an expert in a topic, but there will be some small groups of people somewhere around the world that will keep introducing new things or studying new things, right? Making new connections, right? That raise more questions, research questions, right? That enable us to investigate more and find more answers. Right? So these are questions that actually contributes to the needs and of the society and in the industry at the moment. So Prof. Azman briefly shared with us today about his work on polymer blends, polymer composites, polymer nanocomposites, and his efforts to toughen biodegradable polymer nanocomposites. Prof. Azman downplayed his significant contribution to the world on the work of toughening polymer nanocomposites and also these green polymers, these biodegradable polymers. So his wonderful efforts and achievements in this area owe much praises and recognition actually. So some of the notable work includes the exploration of natural fiber, reinforced biocomposites, and biopolymers for packaging use. His toughening work on PLA has opened doors on exploration of many other biodegradable polymers. So he started with PLA, and then further on he expanded uh, his, uh, his area of scope of materials research into other materials as well. So the problem with biodegradable polymers was it was too brittle, right? So I still remember when I had to make the first composite of PLA. Right? So I brought to him to show him because I was excited. After trying for 3 weeks, trying to make up a sample which can actually resemble the test piece, the first ever test piece for the biodegradable polymer. So I brought to him to show him. I was very excited. But the moment he held the test piece in his hand, it broke like biscuits. So that was the brittle story that I would like to share. Right. So it was in dire need for toughening at that particular time. Right. So apart from his interest in biocomposites, his venture into nanocomposites through the use of MMP, monomerylnite, right, graphenes, further venture into cellulose nanoviscous and carbon nanotubes, has actually resulted in outstanding discovery. So his research career from the start of his PhD, throughout his years as a diligent researcher and academician in UTM, highlights his career development as a scientist and how he has contributed in bringing us all together in this pursuit of knowledge. Now, Prof. Azman's persistence for success is a quality that I personally admire. Right? So once I told him there was a problem I had. Right? Once I told him that I could not find any paper on a particular area of research, on that particular part of research. I couldn't find any paper. He simply replied, it simply means that you did not search enough. Right? So I carry his words until today in all aspects in my career endeavors. So whenever I couldn't get the success that I want, I always tell myself the words that Prof. Azman told me. It simply means that you have not tried good enough. Right? So Prof. Azman has also shown us that collaboration is the key, and his ability to get everyone around him excited with what he does is one of the key attributes of him. Right? So collaboration is very important. Right? So that was the point of time that Prof. Azman shared on the use of cone calorimeter. So at that point of time, no one in Malaysia had that equipment. Right? So through his networking capability, right, we caught the equipment, right, in Turkey, and through our collaborative work, we could perform the experiment from there. That was not the only case for cone calorimeter. At that point of time, somewhere around early 2007 and 8, okay, we also had limitations on transmission electron microscopy usage or preparation of samples through microtome, right? So due to our polymer samples that need to be microtome at cryo or very low temperatures, right? So we had to use our collaborators in order to get the experiment done. So there were a lot of good and bad things that I went through for the past 6 or 7 years with him. So of course, paper writing skills, right? Publishing is one of the main thing that I've actually learned from him. Right? So he has actually trained me well enough that I could actually write a paper on my own. Right? So there was, let's go back to the year of 2007 or 2008. That was the beginning of time where people will start to write research papers and start to publish. Right? So at that point of time, it was I know the learning curve was steep, right? So I had to stay back. I had to spend my weekends analyzing how papers are actually written, how graphs are actually drawn, how analysis is actually made, right? So within a short span of time, right, so I managed to gather these skills from him, right, with his guidance, right. So that's why when I went for my National Science Foundation interview for my PhD scholarships, right, I was in a very good position to get the scholarship because of these papers that I had even during my master's study. Okay? I owe this gratitude to him. Right? So his leadership in UTM, as we have seen, he has nurtured and led the polymer engineering department and RMC to grow beyond what it has originally been created for. Right? His achievement in defining UTM as one of the leading centers for polymer research should be noted as well. Right? So at one point of time, we became a powerhouse for polymer research in Malaysia itself. So once again, we congratulate Prof. Azman on his lifetime achievement as a leader, a researcher, academician, and a mentor. His research contributions and research network in advancing knowledge related to polymers and polymer nanocomposites has significantly altered its development cost globally. Apart from enabling Malaysia and UTM to fly high in the eyes of international researchers. So his dedication and his perfection in preparation of his lectures or his seminars is something that we all should take into account too. Right? He's very serious with his work and he makes sure that he delivers the best in whatever he does. So he's definitely a key contributor to our efforts. We hope he will continue his successful journey in knowledge development. On that note, please join me again to congratulate Prof. Azman on his achievements and contribution to science, engineering, and society. He has become an inspiration for many young researchers who wish to make a difference in this world through research. We thank you, Prof. Thank you, Prof.
Okay. Thank you, Dr. Harin, for the insightful revision about plastic. So from both talks, actually we can got the idea that polymers are everywhere in our life. Okay, even you cannot leave home without polymers. Your credit card is made of polymers, plastic as well. Okay, now we reach to the Q&A session. Is there any question you'd like to ask Prof. Azman or Dr. Harin? Any question that you would like to ask Prof. Azman? Okay, Prof, I have a question for you. Can you hear me? Okay, Prof, this is a very common question. During pandemic of COVID, you use a lot of PPE, personal protective equipment, which we know that PPE are made of plastic. They are not biodegradable. So what is your comment
on the use of the mask? On the use of the mask, which is not recyclable?
Yeah, PPE including mask, gloves, those baju depan plastic, all this thing, the apron
Yes.
that we cannot be recyclable, but there are need, especially during COVID, during pandemic like this. What is your opinion about that?
Um, I think thank you very much, Dr. Roha, for the question. I think for the mask, I have seen a research that was being carried out by a university in Malaysia, where they use a chemical recycling method to recycle the face mask and to be used for other applications. There's a possible to be done. I think it will be an interesting work to do, and I'm sure we can do something useful by using chemical to dissolve the mask and to produce other materials. It is possible to be done.
Okay. Next question from Dr. Fatia Ali, I think. It is from UAE. Is it hard to commercialize the research finding?
Yeah. Okay. The nearest that, okay. Thank you for the question on the commercialization of our product. The nearest that we go so far is our research on graphene, where we do collaboration with Nano Malaysia and Proton, and the result is very positive, and the Nano Malaysia is working with Proton now to ensure the use of graphene in few parts in our Proton cars. And I think it will take some time. It will not be quite immediate, but the work is on the way. Secondly, possible that can be carried out is my current research on the production of wollastonite. We are using the hydrothermal method, and we also can use waste material as the starting material to produce wollastonite, and it has good application in biomedical application. So I think the young researchers can carry out this research, as currently I am going to retire soon, this June 2021, but I think the research has potential to be commercialized after we improve and to be able to produce in a large scale.
Okay, thank you, Prof. There's another question. I don't know, it is a question or comment from Prof. Chehusna. Malaysia use non-woven. Okay, Malaysia use non-woven PPE, which is one use. Must campaign for multiple use woven PPE, Prof.
Yes, of course, I would agree with the multiple use of woven PPE. I don't think there is any disadvantage of using this multiple use woven PPE, and so far we have not heard any comment on the encouragement to use the multiple use woven PPE. So I very much agree with Professor Cik Husna that we should highlight this topic, and the use of multiple use woven PPE should be more popular.
Okay, thank you, Prof. Okay, yes, this other question. Could plastic be used in concrete?
Could plastic be used in concrete?
Yes, slab concrete, as a slab concrete.
Okay. it is possible if we use the recycled thermoset material, maybe as one of the component in the concrete. I am not an expert in concrete, but I can see the possibility of using the recycled thermoset material as one of the component in concrete.
Okay, the next question from Joy Audiobunmi. Sir, natural rubber is bioresource polymer, but after processing, it becomes hard to degrade easily. So, what biopath will enable natural rubber to be at least 80% biodegradable? Ooh, the question.
This is quite a difficult question. Maybe it is the use of the curing techniques that we use. We need to develop the curing technique that will enable to overcome this problem. Maybe not using sulfur as the vulcanization agent, but using other techniques that is more green and will make it able to be biodegradable.
Yes, I agree with you, Professor. There are now current research on this rubber. They they replace sulfur base to something else, like epoxy base, like that, to make it at least 80% biodegradable. Okay, we move to the next question from PM Fatilah Ali. This is from UIA. We have many industries in Malaysia that uses polymeric materials. Do they approach the researchers in university, or should the researchers approach them? Amidst all the KPIs need to be achieved by lecturer, what would be the best method for commercializing our research?
Okay, in my opinion, the researchers in the university should contact the industry to make the industry know about the research that we have carried out. But sometimes we have the opportunity also where the industry came to the university and to discuss. So one of my experience working with industry is we work together with Hyperseal, as I mentioned, to improve the activated sealing for the oil and gas industry. So it is one of the good collaboration that we have experienced. And I think both parties should be proactive in contacting each other.
Okay, thank you, Dr. Fatih Ali. And any question from the viewers? Any question from the viewers? Okay, this is another question for you, Prof. How do you think that the bio-based polymers or fillers can replace the synthetic one in terms of performance or cost, especially cost?
Of course, the bio-based filler. Are you talking about bio-based filler or bio-based polymer?
Bio-based polymers or fillers, you know, that use cellulose or natural fiber against the Kevlar, against something, glass fiber. In terms of performance, of course, in terms of cost, production cost, like that.
Okay. For example, the polylactic acid. The price of polylactic acid is still much higher than the synthetic polymers, and one of the ways that being proposed to lower down the process, the cost of PLA is to use the starting material from waste material, okay, from waste material. So this effort should be consolidated, and at the moment it is far from reality. So currently the PLA is being produced from the plants such as corn, which is relatively expensive, and there should be more effort to reduce the cost by using waste material. And in fact, I have written one article on this, on the use of waste material to produce the bio-based polymer.
Okay. Yes, very good answer, Prof. Okay, there's another question from Prof. Hisham and Shashi. Yeah. With the great knowledge of polymers experts in Malaysia, what is missing to make Malaysia as leading country? As now we see new players in the plastic market like Saudi Arabia, Qatar, Egypt, China, and many developing economies.
Thank you, Prof. Hisham, is it? From Hisham?
Yes, Hisham, for Hisham.
Okay. I think Malaysia is also developing their plastic market, especially with the development in Pengerang. New petrochemical industry will be set up, and I've been told that some types of synthetic rubbers will be produced. I think Malaysia is one of the leading. In Malaysia, we are producing polypropylene from Titan Petrochemical, and I think very value-added polymers, the engineering polymers, will also be set up soon in Pengerang. So I think Malaysia is on the way to compete with other countries as well.
Okay. Thank you, Prof. If there's any question from the floor, is any question from the viewers? I'd like to ask Prof. Azman. Okay, it seems that there's no question, Prof. And we thank you, Prof. Azman. Thank you, Dr. Harin. And thank you for all the audiences for staying with us until the end of the program. Best appreciation for those to make this program a success. And don't forget to claim your CPD points. Okay. There's another question before I just want to close the session from Fatia Ali. She's from UAE, professor. Yes. Salam. I'm asking on behalf of Prof. Dr. Hazlin Anwar, how do polymer in context of Malaysia support the circular economy?
Currently, I'm proposing that, as I mentioned, the bio-based polymer, for example, the PHA and the PLA should start by using the recycle and the waste material as the starting point. So this will be good in the context of Malaysia, but there must be consolidated effort from the ministry, from the universities, and from the industry, so that we can work together and to produce real bio-based material which are lower in cost compared to the current synthetic polymer.
Okay. Thank you, Prof. Hopefully that Dr. Fatila Ali can convey the answer to Prof. Dr. Hazlin. Is there any question from the viewers? Okay. Otherwise, that's all. Thank you, Prof. Thank you again, Prof, for the insightful lecture you've given us today. And hopefully, after the program, all of us will look at the issues of polymer and plastic from different angles. Okay, we have issue with the single-use plastic. We have issue with the sustainability, all because of the issue on the polymers. Okay, that's all. That's all for today. And don't forget to claim your CPD points, like I said. And inshallah, we will meet again in future. That's all. Assalamualaikum. Bye-bye.
Susah